Hey everyone, thanks for joining. John here, senior software engineer with 10 years of experience. I'm the lead maintainer of latterly.io, which is a website that helps you land your first or next programming role. One part educational platform, one part social community. You can sign up for free and join the Discord. And I practice what I preach. I am on the job search myself, having been recently laid off. And today is my first interview loop day. And so one of the techniques in the Kata, which is blog article 3, is that you exercise the kata before the loop to help put you in the right mindset for your interview. It helps you stay focused, fights jitters, refreshes your brain so that certain algorithms are top of mind. And that's helpful because in a typical loop, you'll have a coding round. In terms of timeline, that could be a useful data point for you. This is June 4th, so I was laid off effective May 20th. So this is 2 weeks from having been officially laid off. I'm having my first full loop. I was given my notice of layoff about a month ago. So 1 month from notice or 2 weeks from effective layoff. So I think we're making really, really good progress. And with that, let's kick off. The first one will be straightforward warm up with TwoSum. I'll wipe the existing solution and read the problem out loud. Bathsheba, thanks for the likes. Thanks for being here. So this is number 167, TwoSum, the form where the input array is already sorted. We're given a one-indexed array of integers called numbers that is sorted in non-decreasing order. This could allow for repetition. So I might have a run of ones, 1, 1, 1. That's non-decreasing order. So given numbers, we want to find two numbers within numbers that add to a target. They should be distinct. We can call them index 1 and index 2 of numbers, where it's somewhere between the boundaries of the array. We want to return the indices as a list form that is always linked to. It's a list form that is always linked to. And tests are generated so that there is exactly one solution. We don't need to worry about the sad case where there is no solution, and we don't need to worry about the complicating case where there might be multiple solutions. Great. Intuition. Once array is sorted, I can apply pointer methods to narrow in on the target. No, you can't go outside without an adult, so you can wait for your mom. By starting from either edge. In the worst case, I'll scan every element. So time complexity is O of n. But space complexity is just O of 1 because pointers. So we'll start with left, we'll make a right. Right is pointing to the other edge. It's the length of numbers minus 1. Our while condition will say while left is less than right because we're dealing with a sum of 2. So that if right were to move to the left of left, then I would have the same duplicate sum that I've already computed. For example, 1 plus 2 is equal to 2 plus 1. It doesn't make sense to redo the math. We'll just exit. Captain Falcon, welcome, welcome. Use a hash map. We're also creative, aren't we? Okay, so while left is wherever it is and where right is wherever it is, what is our current sum? It's just going to be left plus right within numbers. And let's compare the current sum to the target. We have 3 possible cases: above, below, or it's a match return. We can just say it's a match. We want to be careful to return the one indexed form. Given that left is initialized to 0, we want to add 1 to that to get the correct answer. Same for right. What if we are too far to the right? How can I decrease my sum of the 2 pointers? Given that right is to the far right, left is to the far left, I'll move left up. No, that won't work. That'll just increase it. I'll move right down. And the inverse if we need to increase the combined sum. Above is a pseudocode. The literal will be the current sum is above the target, and below, we're below target. You would have to sort first. The list is already sorted. Great. If you're finding the video interesting, I hope you'll tap like on the video so the algorithm will send it to other interested people. Follow the page and let's move on to threesum, the next problem in the kata. Threesum reads, given an integer array called nums, let's return all of the triplets. The ijkth values in nums. So these are not indices we're returning the values. Such that ijk must be distinct. You can't have two indices that are duplicate. We could have two values that are duplicate as long as they're at different indices. And the sum ijk is 0. Example 1, we can see that we're allowing for possible multiple solutions. So we won't want to prematurely short circuit. And example 2, we can see we need to deal with the sad case where there might be 0 solutions. So intuition, we can sort, then apply an inner two-sum along with an outer complement. This costs O of 1 space complexity. The time complexity is two-sum times n, which is O n squared. We need to sort to do this. So here I'll say nums.sort n log n time complexity isn't binding. Okay? So it isn't a binding time complexity. O n squared is slower asymptotically than n log n. So the n squared identification dominates. New York, Bronx, thanks for the follow. So this outer complement, we'll calculate that. We'll make a pointer that's called far left. Start that at 0. Say while far left is less than the length of nums minus 1. Complement is far left of nums. It's actually the opposite of the far left of nums. What is a complement? The complement is the thing which will add to form 0. That's why it's relevant to the problem. It's the thing which will add to form 0. So we want to have 3 numbers forming 0. So we take the outer, we take its opposite, and supply that as a target to the inner two-sum. Then the inner two-sum will hit the target. The combination across 3 will be 0. Deshaun, thanks for the follow. Hydro, thank you for your follow. If you're enjoying the video, feel free to tap the screen to give it some likes. And if you're on TikTok, you can go to the bio and find the link to YouTube or Twitch where you'll be able to see the full screen. Okay, so here we want to call to some. We want to fast forward dupes. And then we want to return results ultimately. So let's make sure that we define results. Results is going to be a set. Set for auto dedupe location of tuples. So we're going to provide tuples into the set, not lists or arrays, because lists are not hashable in Python by default. You might be able to do something different in a different language. In Python, it's like a great combination to combine a set and a tuple there. Okay. So here I'll just call self.toSum. And then to fast forward the duplicates, I want to say while complement is unchanged, far left plus equals 1. That's how we're going to fast forward. That's a pseudocode. We also need to make sure that we are in bounds. Oh, I don't want to do -1 there. Sorry. It's just less than nums. Okay, so first let's make sure we're in bounds. We don't want to fast forward and go out of bounds. The bean says, enjoy the day, drink the water. I'll be very, very happy to relax after my full loop today. In the meantime, I have water on standby. I have some electrolytes in this one. And I should also be working on my caffeine as well. Don't want to overdo it, but want to arrive sharp. Shout out to Celsius. Let me know if you want to sponsor. Wouldn't that be great? I would love to have a Celsius sponsorship. That'd be awesome. So how do we know that the complement's unchanged? Well, how did we construct the complement? We can use the same expression basically. So if this value is equal to the complement, then it's unchanged and we can continue to iterate. So that's the approach there. I think now we just need to define toSum and provide the arguments. So we haven't done that yet. Here we're on the solution class, so we will need to make sure that we have the self argument, just because it's a class. What other arguments? We're going to want to pass nums. We're going to want to pass far left. We're going to want to pass results. We're going to want to pass the complement. I think that's about it. I don't know if there's any other data even available to pass. Just pass everything. Why are we passing far left? Because my toSum, I don't want to explore the entire nums array over and over and over. That's doing unnecessary duplicate work. I want to explore the window that's to the right of far left. So my inner toSum, the left is going to be far left plus 1. Right will still just be the boundary of the array. Is it -1 or is it just length of nums? It's -1. It's -1. We want to make sure that we are within the boundary, which means that we are less than nums. To create a number which is less than nums, we take the length of nums -1. Layla says, I have a question. What question to ask mobile app company that you are looking to hire to make sure? Hey, Layla, I really appreciate the question. I don't want to get distracted from today's main purpose, which is to basically warm up for a final interview loop. Please do join the Discord, and someone there can help you. I might even be able to help you, but it will be later today. Thanks for being here. Thanks for the question. Okay, so we have left and right, and then this is the same toSum that we've basically already done. Thank you for the rows. So we'll say while left is less than right. Get cursum, compare to target, append to results, if applicable. Okay, so what's my current sum? My current sum is left plus right. Comparison involves if above, else if below, else we have a match. In the results case, we want to add sorted tuple. The sorted tuple, I don't need to actually run sort because they will deterministically be in order every time. Far left, left, right. Here I'm working backwards a bit. So I know that in this case, I want to add to results, and then I'm working backwards a bit from there. Okay, so we add this sorted tuple for the deduplication and because of order preservation and requirements of the question. We add this tuple, but these should be the values. So this is far left val, but isn't far left val just the opposite of the complement? Yes, it is. This should be left val, because again, the question is asking for the value, not the index. So here's left val, right val. Well, we haven't quite defined these, so let's go make them. Left val equals foo, right val equals bar. Thank you for the follows. Notice that I'm doing some duplicate usage here, so we'll not repeat ourselves. I'll plug in left val here as well. Okay. Then I want to fast forward dupes. Anything else to do here? Not really. I can go do that now. I can do that now. So here we'll say while in bounds and cache target not changed. We will perturb either pointer, left or right. Either would work. We'll just go with left just to keep it consistent. Okay. So given that we're perturbing left, the cache target needs to be left. So we'll say the left val. So while the left val is equal to what? Nums.left. As we keep incrementing left, if the value is unchanged, we want to continue to fast forward. Layla, thanks for the subscription. Daryl says, I'm glad this came across my FYP. Nice to meet you guys. I'm a CS student that struggles with this. Welcome, you're in the right place. I hope you will visit latterly.io, sign up for free, and join the community. And you can always come and ask questions. There's also an events calendar, which can let you know when the streams will be occurring. The Bean says, you activity job searching, brother. I have a final loop today. So yes, absolutely actively searching. Thanks for the likes, over 500 likes on TikTok. Thank you so much. Quick reminder, you can go over to YouTube or Twitch. The link is in my bio if you'd like to see the full screen. Okay, so inbounds is a pseudocode. The real expression we can use is this boundary condition here. So now we have our fast forward logic complete. Let's do the realization of our comparison here. So cur_sum is greater than the target. What's our target? In this case, it's the complement is the target. And then below, cur_sum is below complement. See how we're doing. I missed a colon. I missed a colon. Bummer. Oh, right. So we have these comparisons, but what do we do? What do we do if we make that comparison? So if my sum is too large, I will decrement the sum by moving the upper value to the left. And if I need to make it larger, I will move my left pointer up. That will make my window sum increase. Cool. Just joined, but why so many lines of code for two_sum? Because they're needed. I don't know. Do you want me to go line by line? Like I've already explained why each line is necessary. I would just be repeating myself. Here's the good news. The YouTube stream is persisted. So if you go over to the YouTube channel, after today's stream, you'll be able to rewatch it. I think the short answer is it's not a basic two_sum. It includes like fast forwarding duplicates. Okay, let's see. And I want to allow room that I can have just like a quiet time before my interviews kick off. So we'll do longest substring. We might get to linked list. We're not going to get all the way through the 12. So we might get through linked list, and just to set expectations, that's about as far as we go. I think we'll not get to the palindrome length list. And we might not even get through these, but let's give it a shot. I'd like to allow probably 15, 20 minutes of quiet time. Maybe 15. I don't know that 20 is necessary. So we have about 20 minutes. Okay, maybe we can do a few problems. Does Latterly have anything for pandas? No, you're welcome to contribute, but there's not an official Python curriculum at this time. For most people, I recommend learning full stack web development to optimize job count, minimize risk on your job search, maximize job search time. Sorry, not maximize job search time, maximize the efficiency of your job search time. Maximizing your job search time is not a good, it's not exactly optimal, is it? All right, so for longest substring, the problem reads, given the string S, let's find the length of the longest substring that doesn't have repeating characters. We can see an example. 1, the output is 3, so they're looking to have a return of an integer literal. We can doubly confirm this by the return type annotation on the method. And in example 2, we can see a case where it's 1 because B. So this is what it means that we want to be without repeating characters. Every time I run into a repeating character, I have to reset a counter, basically. It's also important to notice under constraints, a string of length 0 may be provided. A string of length 0 may be provided. Okay, so intuitively, in the worst case, I will need to scan every character. So target time complexity is O of n. You can just imagine a string that has no repeating characters. You'll have to look at every character. To detect dupes, I need to store scene characters. A set is the simplest structure that meets this requirement. In the worst case, it will contain n-1 elements. So space complexity is asymptotically O of n. So the space complexity would be O n minus 1, but asymptotically that's equivalent to O of n. Great. So here I will have a set. We'll just call it scene. We'll make it a set. The approach here, I'll scan left to right. I'll just scan through them. And since I'm going to scan through every character, I could use a while loop. Do I want to use a while loop? I don't know. I could also do a for n. Let's do this. Let's do for I. I may come back and refactor this. For I n range length s. Cool. I is driving this iteration. So I want to have a left as well. It's basically a sliding window. And then I'll eventually return longest substring length. Okay, so the longest substring length is initially 0. Here I'll say to do, check if I is seen. Then I will store char sub I, that's a pseudocode, but it's fine. The character associated to I, we're going to store that in scene. And then we will want to recalculate latest of this cached longest substring length. And that's just going to be, let's call it right, minus left plus 1. I think it makes to call this thing right. Okay. this is the overall structure. Let's think about how to check if I is seen. So I'll have right char is the right of S. We'll just say if right char in seen. What do we want to do here? Purge and iterate left. Really important that we iterate left. I don't want to say, okay, I'm increasing down my string. Oh, I ran into a dupe. I better backpedal on right. Well, then I'm just going to iterate, backpedal. I've created a cycle. So I don't want to backpedal on right. When I run into a dupe, I want to move left until the dupe is purged. And then I can continue and slide the window. So I think I need a while. I need a while somewhere. Is this the while or do we have an inner while? We can do a while here. While right character in scene. I want to purge left.
Dad, can I play this song in your office?
Nope.
Okay.
Bye. So we get the left character here. And I want to scene.remove left character. Now this presents a possible issue. We might see an issue. Hey, you're trying to drop this left character, but it's not in scene yet. Well, yeah, it should be, because the whole condition here is that it's seen, right? The whole condition here is that right is in scene, so therefore the letter is in scene. So whether we refer the letter via right pointer or left pointer, it's going to be there. It needs to be there, or we never will have entered this. So I don't need to guard against dropping a, there's going to be an error if you try to drop a character that's not in the set. I don't need to guard against that, like tautologically by construction. Okay, so this will get us to the place where left is, this is only ever going to check one left. Let's make sure that we're increasing left. Now we want to plus equals left. Okay. Good. Now, whenever that character is purged from left, I'm moving my left pointer, and we can try the while scene again. And when I exit the loop, my right and my left will be at their updated values. And everything looks good. Here, I will want to now go to scene.add right char. So now that we've purged the dupe, we do want to still note that we've seen the character, but now we've seen it on right, not historically. We've seen it at the latest iteration. So let's see how we're doing. Got the wrong answer. What are we missing? I output 1, we're expecting 3. So what's going on here? One thing I can do is print right, left. I think that's all I need to print, eh? Okay, so right, oh, it goes all the way through as expected. Left, ABC, and then we pop over to 1, ABC, and then we pop over to 1. ABC, A, yep. So left is picking up as expected. Left is on 0, 1, 2, 3. Okay. So the issue is in this 3 case, 3 minus 1, 3 minus 1 plus 1 is the value that I want. So this case does lead to the longest substring that I want. 3 minus 1 plus 1. Right, we're losing the cache. Okay, so the issue is that I need to do this. I need to say you're not just the latest one, you're the maximum of whatever you previously were in the latest one. Okay. And there we go. Raymond says store string in a dictionary char list of indices. That's not necessary. You don't need the indices, right? So the set is simpler. What's up?
I was going to tell you, Mom caught a lizard today. When I found one, the one that was right there, she caught it, and I actually got to pet it.
Thanks for telling me. Hey, I'm doing something important.
Okay.
So
I will do that, okay?
Thanks.
I was just going to tell you so you know what I do.
Thanks. All right, let's see if we can do maybe one or two more. That's longest substring. Now we're on to the linked list cycle. I think this is a quick one. Under commit, over deliver, right? Given the list, it's a singly linked list. We can see that from the type or the class definition on the right. There's next, there's no priv, so it's singly linked. And we're given head, the head node of this singly linked list. We want to determine whether there's a cycle. There's a cycle if the same node in the list can be reached again by continuously following the next pointer. Return true if there's a cycle in the linked list, otherwise return false. In example 1, we have an illustration of a loop of a cycle. So from 3, we follow next, and then 204 is pinged multiple times. Can we be sent an empty list? The number of nodes in the list is in the range from 0 to 10 to the 4. So I can be given an empty list as well. And we also see on the type annotation, head is optional. Head is optional. We'll just take care of that edge case. So if there's not a head, then there can't be a cycle. So we'll return false. Now I'll do the rest of my thinking, being able to ignore that edge case, which is really nice. So here,
This is for you. It's really for you.
Hey, Tina. Okay. So in the worst case, we scan every node like infinite times. That's the worst case. That's just so like there's no really acceptable brute force solution. We need an escape hatch. So how can we know that we've seen this node before? We can use a set or a hash map or something like that to collect seen nodes. Then time complexity is O(n plus 1, which is asymptotically O of n. Because in the worst case, we will run into a seen node on the first iter after an in size loop. Does that make sense? So we go through all the nodes, and then we go one more step, and we go, oops, I've seen that thing. So that's kind of like a pretty obvious thing to do. That would be time complexity O of n. Space complexity would also be O of n. But we can do better. We don't need the cache at all if we detect by collision. So we can use fast and slow pointers. Time complexity is unchanged. Space complexity is now constant. You've also heard this called the tortoise method or tortoise and hare. There's a guy who has a name. I don't remember which one it is. Is it Khan? I don't know. Not to be confused with Kuhn's algorithm. I probably did confuse it. Don't confuse Khan and Kuhn. Yeah, I don't know. Fast and slow pointers. I think is also a much more useful moniker because it puts it clearly into the class of pointer patterns instead of Khan, Kuhn, or whatever. Is it Kidane? I don't know. All these people, and you're like, I don't even know what it means. Okay, so let's make fast is going to point ahead and slow is going to point ahead. We'll say while fast and fast.next and fast.next.next. We need to check 2 iterations forward. That's why it's fast. So the idea between fast and slow is that fast will iterate twice when slow is iterating once. So you only ever need to null check on the fast traversal because slow traversal will be guarded by its lagged construction on fast. Okay, so as long as we're able to traverse 2 steps, we want to go ahead and do that. So fast is fast.next, and slow will be slow.next. Okay, and so imagine 2 people running on a racetrack. At some point, the faster person, who's doubly fast, will eventually loop around and lap them. And that will be like a collision detection. And in that case, we do have a cycle. So we'll say if fast is slow, return true. We do have a cycle. Otherwise, we return false if we get all the way out here. That's the whole implementation. Looking at this while fast, I actually don't need special treatment for head. So it was nice to simplify the problem, but it's ultimately not needed. And I went from 50 milliseconds to 40 milliseconds, so it saved me a little bit of time. All right, we'll try for one more. Why not? That was linked list cycle, was it? Oh, palindrome linked list. Yeah, okay. Let me put on my speed runner hat. So given a head of a singly linked list, let's determine if it's a palindrome. What is a palindrome? Mom, dad, race car, 11, 22, any single digit, any single letter. Here in the example 1, we have 12, 21. So it's the same forward and backwards. We want a Boolean response of true or false. True if it is a palindrome. We'll assume no cycles. In the worst case, I need to scan every node. Really in all cases, average case, best case, I need to scan every node. So target, time, complexity. You're the perfect example of people can't buy experience. How are you? Alfredo, thank you so much. Welcome, welcome. I'm doing well. We'll see if we can get this one done in 10 minutes. Ideally less. So target, time, complexity is O of n. I can cast to string or array, then compare res equals res.reverse, which would require O of n memory, but we can do better. If I flip the second half of the linked list in place, I can solve in constant memory for space complexity. Okay, so the problem is marked as easy, and the res reverse thing is easy, but this thing that I've outlined is not easy. But that's the optimal solution, so we'll go for that. So here we want to have a fast is head, slow is head. And I'll say while fast and fast.next, fast.next. dot next. Then fast is fast.net, and here we'll put a to do. Fast maybe can check one iter forward. You might be able to get away with just one of those. Okay, so fast.next, and slow is slow.next. Now slow is the midpoint. So here I will say head of second half is self.reverse linked list on slow, and then head of first half is just head, and we'll say while. Let's not call this head. We'll call this node. We'll call this node. So while they both exist, if their values are different, it's not a palindrome. If their values are different, it's not a palindrome because we need symmetry. On these nodes, the value is called .val. So if .val is not equal to this one, .val, otherwise, if we make it all the way through and everything is symmetrical, then it is a palindrome. Let's make sure that we are incrementing our traversal here. And so you can see what's happening is that we are doing a concurrent parallel traversal. So I've got race car. I take that second half and flip it. And now I'm checking the R's, the A's, the C. And I'm concurrently checking if those values are equal. That's how I'm determining if it's a palindrome. So the solution is done with the exception of reversing the linked list itself. So now I have 2 minutes to reverse a linked list. Geez, I feel like I'm in an elite code competition. Maybe I kind of am. So in the standard unreversed case, I'm starting from A and I'm traversing until none. Once I hit the end node, I want to go one more, and that would be a none. The next value on the last node is none. To reverse this relation, the previous case on the first node should be none. That's why I'm initializing a value called priv with a value of none. So the way that this reversal works is I will start at the head that I'm given, which is the slow pointer and the fast and slow traversal through the hole. The fast and slow traversal through the hole means that the slow one will be at the midpoint because it's a 2-to-1 traversal frequency. So slow will be at the midpoint. I pass slow to the reverse linked list. It's now the head of the second segment of that list. It's the head of the second segment of that list. And so I point at it and I say, this is the current node that I would like to point back to a previous node. Then I will navigate and I will flip the arrows of the singly linked list traversal at every stage on current node. At the end, current node will navigate to a none value. That's how I know I'm done. So we say while cur node. So it's navigated to a none value. I don't want to provide the none value to the higher order. That's not useful in my higher order algorithm. I want to provide priv at that time, which will be the last real node with the arrows flipped. So it would then be the head of the reverse linked list. We square? That's the thing we're doing here. Okay. That's why we reverse priv. So here, I want my cur node dot next to point to priv. That's the sort of naive thing to do. The problem now is, how do I say cur node equals cur node dot next? I've just created a cycle. So that's not a good solution. So now that I've solved this, I can't traverse afterwards. So what I want to do instead is I need to create a cached variable that will allow me to teleport out of this loop. So we will call this next node to reverse. I just call it next node to reverse because next by itself is a built-in method in Python. So next node to reverse is cur node dot next. So now that I've cached this, down here, cur node is not cur node dot next, it is next node to reverse. Okay. So what I've done here is I've said on my current node, the next value will now point to the previous value. And I have escaped my loop that I would have constructed otherwise. The only remaining item is to update the value of priv. We need to make sure priv is always current. So priv was none, and now priv should point at cur node before I teleport. Priv should point at cur node before I teleport. Let's see if I got that right. Okay. Well, this has been a lot of fun, y'all, and that's how you reverse a linked list in 2 minutes. I guess I'm qualified to be a programmer now. Thanks for joining. I hope you'll follow the page, like the video, and I'll see you next time